Imagine looking up at the night sky. You see stars, maybe a planet, and the faint glow of our own galaxy, the Milky Way. Now picture something out there so vast, it makes our galaxy look like a speck of dust. This isn't science fiction. It's a real discovery that has astronomers buzzing. Scientists, using the world's most powerful telescopes, have found a colossal, ghostly cloud of gas. This structure stretches across a region of space we thought we knew well. It challenges our ideas about where galaxies end and the space between them begins. The discovery was made in Stephan's Quintet, a famous group of 5 galaxies. For over a century, we've watched these galaxies crash and pull at each other. But we missed the biggest part, a massive gas cloud hiding in plain sight. It's like studying a forest and missing the roots that connect everything. This find forces us to ask, where did all this gas come from? How did it get so spread out? What does it mean for the galaxies within it? It's a clue that our current theories might be incomplete, a signpost toward a deeper understanding of the universe. Every time we find something that doesn't fit, we get a chance to learn something profound. This isn't just about more stuff in space, it's about a key piece of the cosmic puzzle. The universe always has surprises, humbling us and pushing us to explore further. This massive gas cloud is one of those surprises, a testament to curiosity and discovery. We build bigger telescopes, look in new ways, and find things unimaginable a generation ago. The universe is speaking, and we're finally learning to listen. So how big is this gas cloud? Our Milky Way is already huge, about 100,000 light-years across. Now multiply that by 20. This gas cloud stretches for about 2 million light-years. If you placed it in the sky, it would appear larger than 20 full moons side by side. It's one of the largest single objects ever found. Imagine the Milky Way as a city. This cloud would be the size of an entire country surrounding it. The galaxies of Stephan's Quintet are like small towns within this vast, invisible country. This isn't just bigger, it's a different scale entirely. Understanding this scale shows us the space between galaxies isn't empty. It's filled with raw material for future cosmic construction. For a structure this large to exist, it must have been formed by powerful cosmic events, galaxy-scale forces over millions or billions of years. It's like finding the splash pattern from a giant cannonball in a cosmic pond. By studying its size and shape, we learn about the ancient galactic collisions that created it. This structure is a fossil record of cosmic violence, preserved for us to study. The cloud contains the mass of about 100 billion suns, enough gas to form a new galaxy, or several. Yet, it remains a diffuse cloud. Why hasn't it collapsed to form new stars? The answer could hold the key to understanding the life cycle of galaxies. This giant, seemingly quiet cloud is actually a dynamic, mysterious place. It challenges our fundamental ideas about how cosmic structures form and evolve. To understand the gas cloud, we need to understand its neighborhood, Stephan's Quintet. This group of 5 galaxies found in Pegasus is one of the most studied compact galaxy groups. 4 of the galaxies are locked in a slow-motion cosmic dance, orbiting and crashing into each other over millions of years. The 5th is just a photobomber, much closer to us than the rest. These galactic collisions are crucial. They're how galaxies grow and change. When galaxies collide, gravity pulls out long tails of stars and gas, triggers bursts of star formation, and eventually merges galaxies together. Stephan's Quintet is a perfect lab for studying these processes. Telescopes like Hubble and James Webb have shown us shockwaves, starbursts, and tidal tails. One galaxy is crashing through the group at incredible speed, creating a massive shockwave that heats the gas between galaxies. This violent history likely created the giant gas cloud we're now studying. When scientists pointed a new powerful telescope at Stephan's Quintet, they expected some gas, but not a structure so enormous. They were looking for debris, but found the entire ballroom filled with a ghostly fog. This discovery has turned our picture of galaxy groups upside down. The universe is more connected and more surprising than we thought. How do you find something invisible? This giant gas cloud doesn't shine like a star, it's made of cold, dark gas. To see it, you need a radio telescope. And not just any, you need the biggest in the world. Enter China's 500-meter aperture spherical telescope, or FAST. Its dish is 500 meters across, big enough for 30 football fields. FAST is incredibly sensitive, able to collect faint radio waves from the distant universe. Think of it as a giant bucket catching cosmic rain. The bigger the bucket, the more you catch. The gas cloud is extremely diffuse, its signals incredibly weak. Only FAST could pick them up. Astronomers pointed FAST at Stefan's quintet and listened. They detected a specific radio signal, 21 centimeters, coming from a region far larger than the galaxies themselves. This signal is the fingerprint of atomic hydrogen gas. Mapping this signal revealed a structure 20 times wider than our galaxy, connecting the galactic dancers in a way no one imagined. This discovery shows the power of international collaboration and new tools. NASA's Webb and Hubble see invisible and infrared. FAST gives us a different view. By combining data from all these instruments, we build a more complete picture of the cosmos. Science brings people together to unravel the universe's mysteries. What is this gas cloud made of? The signal FAST detected comes from atomic hydrogen gas. Hydrogen is the simplest, most abundant element in the universe, just one proton and one electron. It's the primary fuel for stars, the building block of everything else. Atomic hydrogen means single atoms floating alone, not bonded into molecules. This gas is crucial in astronomy. It's the raw fuel for star formation. Where we find atomic hydrogen, we find the potential for new stars and galaxies. But a single hydrogen atom doesn't emit much light. Its trick? The electron can flip its spin, releasing a tiny burst of energy, a radio wave at 21 centimeters. This signal is weak, but there's so much hydrogen that together it becomes detectable. The 21 centimeter line is one of astronomy's most important tools. It lets us map the invisible, track the motion and quantity of star-forming fuel in galaxies. It's how we measure galaxy rotation and search for hidden gas. The discovery at Stefan's quintet is a spectacular example, revealing a reservoir of this fundamental ingredient on a scale we've never seen. It's a new window into the universe's hidden structure. Here's where things get even more interesting. Astronomers expected this giant cloud of atomic hydrogen to be cold. After all, it's far from any stars. But some of it is surprisingly hot, which was a major puzzle. The answer lies in Stefan's quintet's violent past. A galaxy plunging through the group at millions of miles per hour, creating a gigantic shockwave. This shockwave slams into the gas, heating it to millions of degrees. But atomic hydrogen isn't supposed to survive in such heat. It should become ionized, turning into plasma. So how can we detect the 21 centimeter signal from neutral hydrogen in a region filled with superheated gas? One possibility, the cloud is a turbulent mix of hot and cold gas with dense, cool clumps surviving inside a hotter medium, like ice cubes in hot tea. The shockwave might be slowly eroding these clumps. This means the intergalactic medium is far more complex than we thought. Solving this mystery will teach us about the physics of gas and the aftermath of galactic collisions. This discovery could rewrite how we think galaxies form and evolve. For decades, we've focused on what happens inside galaxies, thinking the space between them was mostly empty. Now, we see enormous reservoirs of gas lurking in that empty space, especially around interacting galaxy groups. This changes our view of where galaxies get their fuel for growth. A galaxy could gather gas directly from a giant reservoir like this, fueling new stars. It also challenges our ideas about what happens to gas during galactic collisions. We never imagined it could form a single, coherent structure this large. This could help solve the missing baryon problem. Much of the universe's normal matter is unaccounted for, and giant clouds like this may be where it's hiding. There could be many more of these out there, waiting to be found. The story of galaxies is far from complete. Every discovery answers one question but raises a dozen more. Are these giant gas clouds common, or is this one unique? Astronomers will need to survey other galaxy groups to find out. What will happen to this enormous reservoir of gas? Will it collapse into a new galaxy, feed existing ones, or disperse? We need higher resolution observations to see the fine details. Are there dense clumps of cold gas? And how is the gas moving? This discovery reminds us we've only scratched the surface of cosmic understanding. It highlights the need for new technologies and telescopes to see the universe in new ways. Each new window reveals a more spectacular, surprising view. The next great discovery could be just around the corner. So, we end where we began, looking up at the sky. Now, when you look up, think about this giant ghostly cloud, 20 times bigger than our Milky Way, born from a cosmic dance. This discovery is more than an astronomical curiosity. It's a lesson about the universe and our place in it. The cosmos is more interconnected and mysterious than we ever knew. This story is a testament to human ingenuity and our drive to explore. We build incredible machines like fast, not for profit, but to know and understand. Science is a journey we all share, connecting us across borders. You are made of stardust. The same hydrogen in this cloud is in you. The universe is vast, ancient, and full of wonders waiting to be found. The journey has just begun. What do you think we'll find next?